In this video, we'll be looking at another graphing example of rational functions. One more time, to graph rational functions, we have to go through all the details of information, eventually get down to a table of values where we're plotting points in between every important piece of information, and then we'll go ahead and graph the function. So the first thing we're going to go ahead and do is find the discontinuities. Those discontinuities specifically will be attached to the domain, and that domain will be attached to looking at the denominator equaling to 0. In this case, if you set the bottom equal to 0 and solve, you'll have x squared minus 9 equals to 0. That's going to give you x equals to plus or minus 3 when it's all said and done. So my domain is x cannot be those numbers, plus or minus 3, and therefore my discontinuities are x is equal to plus or minus 3. After that, I'm going to go ahead and identify very clearly my x-intercepts and my y-intercepts. The importance to finding the domain first one more time is specifically being able to remove information whether or not it should actually be there. Again, there could be a value in the domain that also ends up appearing as though an x-intercept or a y-intercept, and we need to make sure we remove that from the possibility. If it's a domain issue, we shouldn't have it as a value as an x-intercept or as a y-intercept. So in this case, to find my x-intercepts, one more time, we're going to set the equation on top equal to 0, meaning I'm going to have 2x squared equals to 0. I'm just simply going to solve that, giving me x equals 0. If x equals to 0, I'm going to go ahead and have x equals 0 and my y equals 0, which ends up just telling me that my x-intercept is also a y-intercept in this case. If I were to set this function equal to 0, I'm going to have the same situation. If I plug in 0 for all my x's, I'm going to have 0 divided by a negative 9, and therefore I'm still going to have 0. So my x and y-intercept are actually the same point, which is perfectly fine for this particular set of examples. Now, after we've identified my domain, my discontinuities, my x and y-intercepts, I'm going to have to identify what type of discontinuities they happen to be that between a whole or a vertical asymptote. So for this particular case, again, we're going to go ahead and set everything in this rational function. We're going to go ahead and factor it, but the top doesn't factor at all. And the bottom, x squared minus 9, factors into x minus 3 and x plus 3. And x minus 3 and x plus 3 on the bottom will not cancel out with anything that's on the top. Again, for it to cancel out, it has to be exactly the same as this entire factor x minus 3. And there's no x minus 3 on top. So with that being said, the factors can't cancel out, and if the factors can't cancel out, they're not wholes, and both of those discontinuities happen to be vertical asymptotes. So I have x equals positive 3 as a vertical asymptote, and x equals negative 3 as a vertical asymptote. Now that we find the vertical asymptotes and the wholes, we have to identify the horizontal asymptote and or slant asymptote if there is one. Remember, for us to have a slant asymptote, the numerator has to have a value, a power larger than the denominator power. So because the powers are the same, we don't actually have any slant asymptotes. We'll just go ahead and look at the powers. If they're the same, we have y equals the power on top, its coefficient divided by the power on top and the bottom being the same, its coefficient. In this case, 2 over 1, and therefore y equals to 2. So now that I have all this information identified, I'm going to go ahead and sketch myself a graph with that information in it. This being 0, 0, my vertical asymptote at 3, 1, 2, 3. At negative 3, 1, 2, 3. And at y equals 2, 1, 2. So I have my asymptotes clearly drawn. Now make sure that if it helps, you do x and y to clearly identify which of the lines that are on this paper are your x and y axes. That way you don't get them confused with your horizontal and vertical asymptotes. Now, with all that drawn, let me go ahead and try and pick some points. Now remember, when you're doing this, it's best to go ahead and create a sideways table, generally below your graph, and pick points that you, again, have in reference. So the first reference point I have is a negative 3 for my x. I know that's a vertical asymptote. I want to leave a space between that and my x and y intercept, 0, 0. I'm going to go ahead and leave at least a space between that, and I'm going to go ahead and then draw a positive 3 for my other vertical asymptote. I'm going to leave a space there. And then what I'll do is I'll go ahead and just leave some empty spaces in here. Again, we might not use all these empty spaces, but leaving enough empty spaces gives me some leeway to pick more points if I need more points to see what the graph is doing. So with this all done, I'm going to go ahead and just start picking some numbers. Now maybe I say negative 6 is a good one, negative 5, negative 4. Again, we might not use all these, but we might need all of them to better understand what the graph is doing. I could easily do negative 2 and negative 1, positive 1 and positive 2, and then 4, 5, and 6 over here. Now again, after doing enough of these examples, you can start to make assumptions about the way the graph is going to behave. But in some circumstances, you don't want to make any assumptions. Plot as many points as possible. So, with that being said, I'm going to start with the middle values in here because they're smaller and generally easier to deal with. So if I plug them into either this function or this function, it doesn't matter which one, but you're going to want to get an idea of what the function is going to do. I'm going to plug it into this one. So when I plug in -2, that's what I'm going to start with. I'm going to have 8 on top, all positive. I'm going to have -5 on the bottom, and then times a +1. So I have 8 divided by a -5 is what I'm going to end up having. And I'll put that, again, right here, 8 over a -5. If that's the case, it's going to be -8/5. So that's approximately -1 and some change. Giving me that, I can go ahead and plot that point somewhere down here, -1 and some change. So there's 1, there's 2, give or take. Let's just put it right in there. It doesn't have to be perfectly accurate, but it has to be at least representative. If I go ahead, I'm sorry, that's -2. That's over here. We'll put an X there because that shouldn't be there. Now when I go ahead and plug in -1, that's going to be a +2 on top. This will be a -4, and this will be a +2. So I'm going to have another negative number, and it's going to be 2 times 4, so 8, and then 2 on top. So it'll be 2 over 8 is going to be 1/4. So I'll have 1/4 there, which is definitely a lot smaller of a number and much more closer to the x-axis. So if this is my -1, it's going to be somewhere relatively close to here. And hopefully this kind of makes sense about how this graph is going to be. Now, one thing that's going to help in terms of understanding what this function does is understanding the fact that this section here, this asymptote here, doesn't actually exist there. It's possible that it can, but this set of functions, this information, it doesn't actually get limited by this. The horizontal asymptote, all it does is it guides the edges of the graph. So if I start plugging in 1 and 2, you can't make assumptions that it's going to come up and come back down. There's nothing saying that it has to do that. It can very easily come up and then pass through this horizontal asymptote. Again, we can't cross vertical asymptotes, but in some very special circumstances, we can cross horizontal asymptotes. So if I start plugging in 1 and 2 as my values, it looks like I'm going to get 2 divided by -2 and 4. So I'm going to have a negative, looks like 1/4 again. So it does look like it's going to come back down. If I plug in 2, let me just check, 5 and -1, sure enough it's going to be negative again, and it looks like it's going to be 8/5 all over again. So it looks like on this side here, and again those values I'm just plugging into a calculator, I'm not doing it off screen, I'm just using my brain for those, but again the best way to do that, the safest way, is to go ahead and just chuck them into a calculator. So it looks like what this graph is going to do is come up like this, and then come back down like this. Again, be wary that sometimes, again, these things do bound around and change. So it's safest for us to understand that these things could and don't necessarily remain in the format that they're in. So, with that being done, the next thing we're going to go ahead and do is start plugging in 4, 5, and 6, and -4, -5, -6. But based on the understanding of the way that these functions work, there is a really smooth way to understand the behavior of a function around a vertical asymptote. It's very much similar to that of your x-intercepts. In most functions, if your x-intercept occurs twice at a certain polynomial function, then it should bounce at that location. You'll notice here that this x squared tells me that the x equals 0 x-intercept does actually occur twice in this function, and sure enough, it touches that point and bounces away from it. That same concept can be said for your vertical asymptotes. If the factor of x minus 3 in the denominator occurs more than once, there's a good chance that the function will approach this in the same direction if it's an even power of that factor, and it will alternate if it occurs in an odd power. So I can argue that this graph should look something like this in the grand scheme of this problem. Now again, do not make any assumptions, actually plug in values and notice how the function is going to behave. So if this is the case and I plug in 4, I'm going to have 1632, and then it's going to be 32 divided by 1 times 7. So it's going to be 32 over 7, which is a relatively large positive number, closer to 4. I'm not going to write that in here, but I am going to write 32 over 7, and that's going to be somewhere above this this dotted line of y equals 2. Because again, 32 over 7 is somewhere close to, if I do 7 times 4 is 28, that's going to be 4 and some change for 32 over 7. So being 4 and some change, 3, 4, 5, it should be somewhere way the heck up here, which does make sense for number 4. And I mean, I might have not drawn it accurately, but it does work out. And you'll notice that if I plug in the negative 4, the actual exact same thing is going to happen on this side. So again, the idea is to make sure that we graph as many points as possible to better see how everything's going to behave. Now, the last thing we didn't do in the previous video, but we're going to do in this video, is talk about symmetry. Again, remember, symmetry is something that we can do with all functions. And it's the concept of plugging in a negative x to the function and seeing what happens. What do we get back? In this case, if I plug a negative x in, this squares out and disappears the negative. This squares out, disappears the negative, and this doesn't get the negative at all. So in this case, f of negative x ends up being equal to the original function altogether. And if we recall what that symmetric rule states, it states that if f of negative x equals to the original function, this function should be even. And if this function should be even, that also implies symmetrically that we should end up having symmetry over the y-axis. And if you look very carefully at this, you'll notice that if I fold along the y-axis, this side is exactly the same as this side. I do that carefully right there. Okay, so folding it like this, you do get the exact same function, and symmetry helps us reinforce that we've done this correctly. Again, making sure that anytime you're graphing a rational function, you go through the domain first, x and y intercepts after, holes and vertical asymptotes together, horizontal and slant asymptotes together. Make sure you graph yourself all the information and then plot a bunch of extra points to better understand and better grasp how the function's going to behave.